Okay, let's start. So last time, what we did was the introduction of the ramification filtration on the Galois group of a finite extension, Galois extension of a P field, right? P is a prime number, K is a P field, so K is complete for a discrete valuation. With finite residue field, right? Of characteristic P. That's what our field K is. L is a finite Galois extension of this, and G is the Galois group of L over K. Then what we had defined were these subgroups. No? G minus 1 was equal to G itself, and it contained G naught, which we call the inertia subgroup. Then it contained G1, which is the ramification subgroup. And then there are these higher ramification subgroups, Gi for every I. Okay, so what we had proved was that these are compatible with the passage to a subgroup. What that means is that if I have a subgroup H of G, then of course I have L here, then LH here, and K here. So this group is G, but this group is H here, right? So the ramification filtration is defined for H as well. How is H sub I related to G sub I? And the simple answer in this case was that H sub I is just the intersection of G sub I with H. So that's a very simple kind of a thing which is going on. Now, we had also defined this JG of S for S in the group G, and it was the valuation VL of Sx minus x. So that, of course, was where x is what? X is any element such that OL is equal to OK adjoint x. And we had proved that there are such elements, right? X is any such element, and this was independent of the element x that you choose. For a normal subgroup, when H is a normal subgroup, then of course this is also going to be Galois, and the Galois group here is going to be G mod H. So for S in G, we have S bar in H, and you know this, the function G, rather J sub G encodes this filtration, right? The filtration is here, and it is encoded in the function J sub G. So we would like to know what is the filtration on the quotient G modulo H. How is it determined from the filtration on the group G? or equivalently, how the function j for g mod h is determined by the function j for g. And this is the relationship which we had proved last time. So here is the ramification index of L over LH, this of this extension, and then J of G modulo H of S bar is this sum on the right. The sum over all T in H of JG of ST. On the left, we have S bar, and then we have to look at all the pre-images of S bar. They are all of the form ST for a T in H, and S is one of the pre-images, right? So today, what we are going to do is to introduce the upper numbering of the ramification filtration. It is a different, I mean, essentially it's the same filtration, but the numbering is different. The indexing is changed. And it is changed in such a way that for the passage to the quotient, the formula is simpler. So in the upper numbering, what we will have is in the upper numbering, we will have G mod H V. This is the upper numbering. This is the upper numbering is going to be just the image of G GV, that's the upper number, V is the upper index. The image of this in G mod H of the index of this subgroup GV. So let's start doing that. So the first step is to define G sub U, not just for integers U. Just now, till now, we have just defined G minus 1, right, which is G. Then we have G0, then we have G1, which contains G2. So we have defined these G sub I for all integers I. Now I want to define it for all real numbers. Take any real number U between -1 and, greater than -1, and you define G sub U to be G, this is called the ceiling, right? Ceiling of U, that is supposed to be the smallest integer, which is greater than U. So here's the real line, here's your U. There's always an integer such that U is between M and M plus 1. Then this U is, of course, going to be M plus 1. And U is equal to M if U itself or is equal to U, whatever. It's equal to U itself if U is an integer, right? Otherwise, it's strictly between two integers, and it's the one which is bigger than U. Okay, and so this definition is equivalent to saying that an element S is in G sub U if and only if what I'd call J sub G of S is greater than U plus 1. Okay, so till now we had this for integers, for U an integer, but now it is valid for any real number U, which is greater than -1. So that's one thing which we have done. defined GU for all U of this kind, not just for all real U of this greater than -1, not just for integers U. The second thing you do is to define this function phi L over K of U. U is again a real number between greater than -1. And you define this function phi at U to be the integral from 0 to U of this index, index of the subgroup GT in G0. Now, that is true if T is greater than 0, then of course, GT is actually a subgroup. So there's nothing to explain. But what happens for T between -1 and 0? What happens for these? So here is the answer. For T in this interval, of course, this GT is not a subgroup of G0, and it contains G0, right? So you adopt the convention that this index is actually equal to this if T is -1. It is the if T is -1, then you have G -1 and G0 is a subgroup. So the index of index in G0 of G1, you just define it to be 1 over the index, G -1, the index in G -1 of G0. That's what I've written here. But if T is not equal to 0, which is not equal to -1, which is to say if T is strictly between -1 and 0, then this GT is actually equal to G0, and the index of G0 in G0, I mean, that's just equal to 1. It's not even a question of any convention. So, but the point is that the thing to remember is that phi L over K of U is defined as the integral from 0 to U of dt over the index in G0 of GT. That's just, by the way, the function which is being integrated is the function T goes to 1 over this index is, I mean, it's constant, it's basically constant with a few jumps. So if you were to draw the graph, it will look like, some function like this, then like this. So it's a step function, maybe that's the name. I don't remember. Maybe it's a, step function, perhaps.
Yes, sir, it's step function.
Except that, that looks like a correct picture. Okay, so let's be more explicit. If m is an integer and u is between m and m plus 1, it's a real number, right? U is a real number between m and m plus 1. Then by definition, this is by definition, the value of the function phi L over K at U is 1 over G0 times this sum, G1 plus G2 up to Gm plus U minus M times Gm plus 1. And where Gi is the cardinality of G, of the group Gi. And that's clear from this picture, right? Here is your U, here is, let's say, M, Here is m plus 1, and this integral is phi, and now this integral you can just compute because this is a step function. So, excuse me. Okay. So in particular, if this u is an integer, if u is equal to m, then this last term drops off, and the formula you get is that phi L over k of m is 1 over g naught summation over all I in the interval 1 to m of gi. Gi, recall, is the cardinality of the group gi. And G is, of course, the Galois group of L over K. That's why there's L over K here, and that is the same L over K is here. And of course, you can rewrite this. You add 1 to both sides. Then here you are adding G naught upon G naught. So the count can start from G naught instead of from I equal to 1 to m. It can allow it. So that's the formula which we will be using sometimes. Phi L over K at an integer m. This is an integer, let's say greater than 0, right? Is so not this, plus 1 is equal to 1 over g naught. The sum over all I from 0 to m of the orders of the groups G sub I. That's it. I mean, that's how this function phi L over K is defined. Okay, so this function is continuous. You can see that it's continuous. It's piecewise linear because it's the integral of a step function. The function looks like something like this. So the integral will look like, I don't know, this, and I mean, it's a piecewise linear function, and it's increasing. Increasing because, of course, it's computing the area, and the area keeps increasing. Phi of 0 is 0. That is that's clear because it's the integral from 0 to 0 of something. Now, the derivative, the left derivative and the right derivative of this phi. So this function phi L over K will sometimes be simply called phi, right? Phi L over K is the full name. Sometimes we'll just abbreviate it to phi. Just as here, we have already done it. Now phi L prime and phi R prime are the left and the right derivatives of phi. Then what this says is that the left derivative and the right derivative are both equal to 1 upon g naught, the index of gu in g naught, if u is not an integer. And the left derivative is this, and the right derivative is this, if u is an integer. That's clear because, it's only at integers that this function has jumps, and therefore the function phi will be it's not discontinuous. It's not differentiable. All other places it's actually linear. Only at integers has it the chance, or is there a possibility that it's not differentiable? I mean, it may be differentiable. There's nothing to prevent that nothing to prevent gu from being equal to gu plus 1. That can happen. But if gu is different from gu plus 1, then, or if gu, let's put it this way, if gu is different from gu plus 1 for all u plus epsilon for all sufficiently small epsilons, then u has to be an integer, right? So anyway, what this says is that if this phi, the function phi, is differentiable at every u which is not an integer, and at integers u, the left derivative is this and the right derivative is this. Okay, so all this says that this function phi is a homeomorphism of this -1 to infinity. I mean, this of this interval. You have 0 here, -1 here. So it's this interval -1 to plus infinity, and onto itself. That this function phi L over k is a homeomorphism. Of course, that homeomorphism depends upon the extension L over k. You should try to see what happens when L over k is unramified. That is perhaps going to be a completely simple case, because in that case, G naught is going to be equal to the trivial group, right? And so just try to see what happens in this simple case. Also, yeah, here could be some exercises. Compute this function phi L over k for k equal to qp and L quadratic extension. QP, right? So in order to get a feeling for what these functions are, you should compute these special cases and see what you get. Okay. So because it's a homeomorphism, there's the inverse map. And we'll call it psi L over k. This is the inverse of phi L over k of this homeomorphism. So we could say this is phi L over k inverse. Not 1 over phi L over k. I mean, it's sine inverse is not 1 over sine. So it's the reciprocal. Okay, what about the function psi that we have just defined? It's also continuous. It's piecewise linear and increasing. Its value at 0 is 0. And if v is equal to phi of some u, then the left derivative at v is equal to 1 over the left derivative of phi. Oh, not the left derivative. I think it should be, no, we don't. It doesn't make sense because phi L should be the derivative, right? Let me just. Yeah, so it has to be the derivative. It's the derivative here and the derivative here, because otherwise the left and right doesn't make sense, right? So, so the left derivative of psi at some v, which is phi of u, is 1 over the left derivative of phi at that u, and similarly the right derivative of psi at the same v is 1 over the right derivative of phi at the same u. So in particular, the So just recall. Now, if you recall that, this phi L prime of u, that was some integer, or it was 1 upon an integer, right? Yes, here it is. It was 1 upon, this index is an integer, so the left and the right derivative are 1 upon some integer. So these CL prime and CR prime are integer valued. Because it's 1 upon something which is 1 upon an integer. Okay? Now the important thing is that if v is an integer, then so is u, which is psi of v. Now, the first three things that are noted here, this A, B, and C, they are kind of obvious. So I'm just leaving them for you to verify. Let's check this part D. And it says that if V is an integer, then U, which is defined to be psi of V, is also an integer. So how do we prove this? We have to prove that U is an integer, but in general, I mean, it has to lie between some integer. It has to lie in some interval like this, between an integer m and m plus 1, right? Now we know how to compute phi of u for something between m and m plus 1. Phi of u is, first of all, phi of u is equal to this v, right? If I apply phi to both sides here, I'll get phi of u is equal to phi of psi of v, and which is equal to v, because these two are inverse functions. So now come back here. We have phi of u is 1 over g naught times this sum, right? That's what we had shown earlier. When, let me just go back and show you where it was. Here it is. This or this, I mean, there. Maybe this one. This one is the one which is relevant. Phi of u is this thing here. So that's what I've rewritten. G naught times phi of u is g1 plus all the way up to gm, and then u minus m times gm plus 1. Okay? We have this formula. Now, this gm plus 1 is the order of the group gm plus 1. And that's a subgroup of g naught, g1, and gm. The orders of these groups are these numbers, this, etc. And this here, g naught is here. So this gm plus 1 divides all these numbers, this one, and this one. So let's divide throughout by gm plus 1. So if I divide throughout by gm plus 1, I'll get g naught upon gm plus 1 times v is equal to g1 upon gm plus 1 plus gm plus 1 plus, what's that? U minus m. That's what I will get if I divide throughout by gm plus 1. Remember, these are all integers. So is this by hypothesis. So we know that everything except perhaps this last one is an integer. And in the last one, this m is, of course, an integer, because you took your u to be something which lies between the integers m and m plus 1. So everything, all these things are integers. M is an integer, therefore this u has to be an integer, right? Right? U minus m is an integer, and therefore u is an integer. Okay, so that was a proof. Now we define the upper numbering of the ramification filtration. So G upper V, for some V which is greater than -1, real, huh? Any real number V between greater than -1, you define G upper V to be G lower psi of V. This should not be confusing. Here is another way of expressing this. So this is just saying that if V is equal to phi of U, then what is it? Psi of V is equal to U. Yeah, so this gives you another equivalent way of expressing this, that G or upper phi of U is equal to G lower U for every real U greater than -1. Okay, so that's the definition of the upper numbering. So we have got subgroups basically for all for GU, U greater than -1, U real. These are all subgroups. What I should call them decreasing subgroups of G, and that's what a decreasing filtration is. Huh? It's a decreasing filtration, but it's indexed by, actually when you're using, yeah, U is not a good, let me use V here. So GV for all real V greater than -1, these are all subgroups, and they form a decreasing family of subgroups. And you can check that G -1, G upper -1 is just the whole of G. G upper 0 is just the inertia subgroup, right? And G upper V is trivial for V sufficiently large. Okay, that follows from the fact that G lower U is trivial for U sufficiently large. Now, another thing which is not very difficult to check is that you can recover the function psi from this, the knowledge of the upper numbering. In what sense? In the sense that psi of V for every, okay, I mean V greater than 0, psi of V is equal to the integral from 0 to V of the index of GW in G0 dW, right? This integral is, that's your function psi. In other words, if you, how did we define? So roughly speaking, we defined phi L over K, and then we defined psi L over K as the inverse function, and then we defined also the upper numbering, GV. So well, both these things, this and this, were defined in terms of this function. Where is it? Here. So this is to say that it could have also been defined in terms of the function psi. In other words, all these three things determine each other. These two, of course, determine each other because they are inverses of each other. And this one here, this integral sort of representation is saying that the upper numbering determines the function psi and therefore also determines the function phi. Okay, so these three pieces of information are equivalent. Okay, and these functions phi and psi have one important property, which is transitivity, which means that if I have a normal subgroup H of G, normal subgroup, so that this extension is also Galois, and therefore I can define phi k prime over k. That makes sense because k prime, only when k prime over k is Galois. For the time being, I have not defined it for other extensions, right? Only in terms of the lower numbering of the ramification filtration have we defined the function phi. So in fact, what I wrote here was I could maybe make that complete that diagram. I had what G sub u minus 1. So it's in terms of this that I defined phi L over k. And then in terms of this, I defined psi L over k. And also the upper numbering. Okay, so there are these four things which carry really the same information, but they are convenient for different purposes. So the idea is that this is good for passage to a subgroup. And this one is good for the passage to a quotient. In what sense? We are going to come back to it and make it more precise. But in what sense is this good, the lower numbering good for the passage to a subgroup? That we have already explained. It just means that if I have a subgroup H, then H sub I or H sub U is equal to H intersection G sub U for all U which is greater than minus 1. So that's what I meant by saying that this one is good for the passage to a subgroup. And similarly, we are going to show that this upper numbering is good for the passage to a quotient. But for the time being, we are proving this basic property of these functions phi and psi, which is the transitivity. So this is the transitivity for phi, and this is the formula which expresses the transitivity for the function psi. Okay. When H is a normal subgroup, so here the group is H, here the group is G modulo H, and the whole group is, of course, G. The second thing, okay, so this is the sense in which the upper numbering is good for the passage to the quotient. It is good in the sense that whenever I have a normal subgroup H of G, the upper numbering on the quotient is obtained from the upper numbering on the group G itself by the passage to the quotient. So in other words, G mod H upper V is just the image of GV. Just as no, it's not G. It's H. H sub U is just the restriction of, or rather the trace. That's a better word. Trace of G sub U on H. And here, of course, the image of GV in G mod H, right? So this, by this is meant, of course, GU intersection H. And by this, of course, you mean, what is the image of GV in G modulo H? It's GV H modulo H, right? Or, I mean, of course, this is also equal to GV modulo GV intersection H, but viewed as a subgroup of G mod H. Yeah. Okay, so we have these two propositions. The transitivity of these functions phi and psi, and the passage to the quotient. We'll come back to these, we'll prove them, but for the time being, let's, not time being, I mean, in order to prove them, we need 3 lemmas. We'll prove these two propositions, and there are these 3 lemmas which are somewhat technical, and they're in the nature of verifying things one after the other. They aren't very deep or insightful, but they are just some verifications. Okay, so the first lemma says that for every u, every real u greater than -1, phi L over k of u is given by this formula on the right. So let's call this function on the right theta of u. There's an u here, and wait a moment. Yeah. So S runs through G, and that's it. Yeah. So this is slightly, I mean, it looks a slightly complicated expression for this thing, which is a simple notation, but the thing on the right is perhaps more amenable to calculation. It's explicit, you can compute it. The left one is just a piece of notation. So how do we prove that the left-hand side is equal to the right-hand side? So they are both functions, phi and theta. One checks that this function theta is continuous, it's piecewise linear, and it's possible to do all this because it's so explicit. Theta of 0 is 0. And if u is between m and m+1, some integer m, then the derivative of theta at u is 1 over g0 times the number of s such that jg of s is greater than m+2, which is the same thing as saying that it's 1 over the index of m+1 in g0. Okay? So these are some verifications which follow from the explicit expression for the function theta. Okay, so what? The point is that all these properties are shared by the function phi. If two functions have the same value at 0, and that they have the same derivative, then of course these functions have to be equal. And that's what we wanted to prove, that this phi is equal to this theta. Okay, that was one. This is the second lemma. If I take a sigma in G mod H and define define J of sigma to be the maximum possible value of Jg of S, where S is in G and S maps to sigma in G mod H. So the maximum possible value of Jg of S over such S. Then J of G modulo H, J of sigma with respect to G modulo H minus 1 is given by this formula. Here K prime is the fixed field of H. Okay, again, this is a very technical statement, but it can be verified, and here is the verification. So take some S which maps to S, which maps to sigma, and such that J of sigma, which we have defined here, right? This J of sigma is the supremum of all such things. So there has to be some S where this supremum is attained, and let's take one such S. Okay, and let's call it M, this Jg of S. Now one checks that if some T is in H, and it's in fact in the subgroup Tm minus 1, Hm minus 1, then Jg of T is greater than M, and therefore Jg of St is greater than M. I don't recall if we had proved things about Jg, relating Jg of S, Jg of T, and Jg of St. We had proved some statement relating these three things. So that must be it's an application of that statement. So it follows that Jg of St is equal to M. Now that was if T were in M minus 1. If T is not in M minus 1, then one checks that Jg of T is strictly less than M, and therefore Jg of St is again equal to Jg of T. So in both cases, what we have is it's either M or Jg of T, and whichever is smaller. So that happens in both cases. This is for all T in H, right? We had started with the T in H here. So either that was one case and this is the second case. In both cases, you have this. And therefore, G modulo H of sigma, this is what I had recalled at the beginning today. We had proved last time a formula for this thing, yeah? This is a proposition which I proved earlier, that it's 1 upon the ramification index of L over K prime, and K prime is here, it's the fixed field of H, and then this thing here. Okay. But Jg, the restriction of Jg to H is just JH. And this is the ramification. Now, the ramification index of L over K prime is equal to, of course, the cardinality of the inertia subgroup of this extension, right? You will have L here and K prime, and H is the group here, and H naught is the inertia group, and this is the maximal unramified extension of K prime in L, and therefore the inertia, whatever, the ramification index EL over K is equal to the cardinality of H naught, right? This is in general. So we have this. So now you apply lemma 1, which I just proved, to this group H, not to the group G, but to the group H. What was lemma 1? lemma 1 said that this, it made some statement about these things, right? And that is what is occurring here. Okay, so you apply lemma 1 and you'll get what you want. Okay, so that proves lemma 2. Then you have this lemma 3, which says that if V is equal to phi L over K of U, then this is the important thing actually. Yeah, then GU, the image of GU, G lower U in G mod H, that's the left hand side, is equal to G mod H lower V. Okay, so this is what we have to prove. This is what is called Herbron's theorem sometimes. So let's continue with the notation of lemma 2. What does it say? It says that sigma is in the image of GU, G sub U in G modulo H, if and only if J sigma minus 1 is greater than U. Now, we have seen that, so this amounts to saying that this, okay, now phi is an increasing function, right? Phi L over K, K prime is an increasing function. So you have this inequality, if and only if you have this inequality, when you take phis on both sides. Maybe it has to be phi L over K prime, perhaps. That's what you're taking on both sides. Yeah, it has to be phi L over K prime. That's right, that's what you use. Yeah. So now we have seen that the left-hand side is this, and this is V by definition, and that amounts to saying that sigma is in G mod H sub V. So I admit that, these things have become slightly technical, but soon we will have proved the statements, and then you just need to remember the statements, which are very simple. The statement that we get are very simple, that, phi and C are transitive. That's one statement. The other statement is that G mod H V is the image of GV module in G mod H, etc. Those things are easy to remember, and these are the things which we will use later. In the course of the proof, we are having to use these somewhat technical lemmas, which are a matter of verification. So now let's come to the proof of the transitivity for phi. That's what it says. For the function phi L over K is the situation is what? K prime, which is L H, and you have L here. So this is your phi L over K prime. In this situation here, and phi K prime over K here. So this is what the transitivity in this case looks like. For C, it looks somewhat different. I think it was C L over K is equal to C L over K prime, C K prime over K. That's what it looks for C. But for phi, this is what transitivity states. So let's take some U. which is strictly greater than -1 and which is not an integer. And what's the derivative of the right-hand side at u? This is the right-hand side. I want to show that it's equal to the left-hand side. So I'm first computing the derivative. And I think when it's using Leibniz rule, so it's going to be at u, it's going to be phi prime of the first function. This is the first function at phi L over k of u. And we are computing the derivative at u. And then this is the second factor, the derivative of the second function, right? So if I'm f of g of x, okay, so let me put it this way. F g prime at x is going to be f prime of g of x times g prime of x, right? I hope this is correct. Okay, so that's what I've written. Now you go back to the definition of these things. So this first factor is equal to this, and the second factor is equal to this. So that is equal to that's what you get by lemma 3. Lemma 3 is what is called the Erbrand's theorem, and this is the crucial thing. So you just need to plug in here to get this equality here, and by definition that's going to be phi prime of L over k. So the derivatives agree. Derivatives agree, and same value at 0 implies the functions agree. So the left hand side is equal to the right hand side. Okay, so that is the proof of the transitivity. For phi, how about the transitivity for psi? It follows from the one for phi, because this is phi is equal to phi inverse. So if you have transitivity for one, you get it for free for the other. So now you have the proof of the passage to the quotient. So which means that, what is it? I have to prove that G mod H V is GV H modulo H. That's what I have to prove. Okay, so what we have is G modulo HV, the left, this is equal to G modulo H X, where X is this. Why? Because that's the definition of the upper numbering. Let's see if the upper numbering has been defined as, where is it? Yeah, here it is. So G upper V is G lower psi of V, or G upper phi of U is G lower U. So one of these two things has been used. Which one has been used? Yeah, the one involving psi has been used. G upper V, or G mod H in this case, the group is G mod H. G mod H upper V is G mod H lower psi of K prime over K V. So G mod H, of course, is the Galois group of K prime over K, because that's L over L, the fixed field of H, and the group here is G mod H, right? So we are looking at the function psi L or not L, yeah. C K prime over K. That's what it is. Now by lemma 3 says that G mod H lower X is going to be GWH by H, where W is C of L over K prime of X. That was lemma 3. But X itself, X is C of K prime over K of some V. So when you plug that in here, you'll get C of L over K V by transitivity, which we have already proved. Okay, so that's so this W is going to be this. So because this W is equal to this, G lower W is going to be G upper V, and therefore now you put everything together. This G lower W, sorry, is G upper V. You put, that's what I've written here. So the right hand side of this is here, and the left hand side of this was the right hand side here, so it's, and the left hand side here. So you put everything together and you get what you want. So that was the main theorem. I think nowadays, I mean, this fact that the upper numbering is compatible with the passage to the quotient should be called Erbrand's theorem. Anyway, but anyway, so now let's do some computations. Let's actually compute these filtrations in some cases. So I'll wait for a few minutes and let's get back to computing it. So if anybody has any questions, they can ask them at this point. No questions? Okay, things must be absolutely clear. Let's continue. So the first thing that we want to prove is that if I have a P field K, and if I denote by QK as before, the cardinality of the residue field, right? And if I take an integer which is prime to P, and then I take the splitting field of T to the n minus 1, which means I adjoin all nth roots of unity. And similarly, I can do that for K and for KK. So I'm adjoining all nth roots of 1 to K or to the residue field. Remember, n is prime to the characteristic of the residue field. So the assertion is that this Kn is an unramified extension of K. The ring of integers of Kn is obtained from the ring of integers of K by adjoining zeta for a primitive nth root zeta. Take any primitive nth root. Of course, it's contained in Kn. It's contained in Kn because Kn is obtained by adjoining all nth roots, primitive. So it's enough to adjoin primitive ones, of course, and it's enough to adjoin one primitive nth root. And the ring of integers is generated as an OK algebra by any primitive nth root of 1. And the Galois group of Kn over K is isomorphic to the Galois group of Kn over K. And of course, this we know, I mean, it's equal Z mod, and that's Z mod GZ. It's cyclic with a canonical generator of order G. And this order we will determine. Of course, I mean, this order G is equal to Kn over Kk. I mean, okay. I've called it Kn. Yeah, Kn. But what is it in terms of N and Qk? So this we will we'll find out. Okay. So here's the proof. What I do, so I want to show that Kn over K is unramified, right? But what I do know is that there's an extension which which I'll call L. There's an extension L over K, which is unramified, and whose residual extension is this one. So let L be the unramified extension whose residue field is K sub n. This we have proved that for every extension of the residue field, there's a unique unramified extension of your P field, whose residue field is that extension, right? So L is this one. Now, remember we have this Teichmüller representatives or multiplicative representatives. So if this Kn is the residue field of L, then this Kn, of course, is not contained in L, no. But it has these representatives, multiplicative representatives, inside L. That's what you have here. And so if I choose a primitive nth root of unity zeta bar in Kn, then omega of this zeta bar, let's call it zeta, that's going to be a primitive nth root of unity in L. But as this zeta bar generates Kn over K, this zeta will generate the ring of integers of L over OK. So OL is OK over zeta, and therefore L is equal to K zeta. In other words, L contains Kn, and therefore they have to be equal. Because Kn is the smallest field containing containing a primitive nth root of unity, smallest extension of K, containing a primitive nth root of unity. Did I not compute? Oh, okay, here it is. Here is the computation of the degree. The degree of Kn over K is equal to the order of Qk in Z mod Nz star. Of course, this we had assumed that N is not congruent to 0 mod P. This is the same as saying that the GCD of N and Qk is equal to 1. And this is the same as saying that QK is invertible in Z mod, in the ring Z mod NZ. Okay, so as an element of this multiplicative group, QK is an element of this multiplicative group. As such, it has some order, and that order is equal to the degree of Kn over K. Of course, this is also equal to the degree of K sub n over K sub K, right? Because this is an unramified extension. Yeah, here it is. The degrees are the same because this is unramified, and this is equal to the right-hand side because for finite fields, I mean, if K is a finite field having Q elements, and if I join K zeta, where zeta is a primitive nth root of 1, then the degree of this K zeta over K is, of course, equal to the order of Q bar as in the group what is the group? Z mod NZ star. Right? Yeah, in fact, not just that. I mean, you could even say that the Galois group of K zeta over K, it is a subgroup of Z mod NZ. Star is the subgroup generated by Q bar. Because the generator of this generated by the element x, which changes every x in K zeta to the qth power. And I mean, this inclusion is sort of to be taken. I mean, it's not strict inclusion in the sense of the elements are the same, but canonical injection is what you should think of it. Anyway, so I have now 15, 17 minutes to go. Now let's do this for QP and see what happens when n is a power of the prime p. Here n is, of course, n is now divisible by p, right? Earlier we were taking n to be prime to p. And now let's see what happens when I adjoin nth roots when n is divisible by p, not just divisible by p, it's a power of p. Let's call it Kn. K sub n is QP zeta, where I'm adjoining a primitive, or K, or I mean, of course, this is K, P to the M is another notation for the same thing. Okay, so this proposition says the following things, that Kn over the degree of this extension is phi P to the M, of course, which is, it's not this phi that we have been discussing just now. This is the order of Z mod P to the M Z star, right? And that's the order. P minus 1 times P to the M minus 1. And the Galois group of Kn over Qp, so here it is equal to, in some sense, canonically equal to Z mod P to the Mz star. This extension is totally ramified. If I put pi equal to 1 minus zeta, then it's a uniformizer of Kn. And finally, the ring of integers is obtained from ZP by just adjoining zeta, is generated over Z as a ZP algebra by zeta. So notice that, I mean, these two statements, 1 and 2, that the degree is equal to phi p to the m, and that the Galois group is the multiplicative group of Z mod p to the m, because the order of this is, of course, phi p to the m. So these two statements, 1 and 2, are equivalent, right? Because in general, when you adjoin p to the mth roots of unity, the Galois group is going to be a subgroup of Z mod p to the m star by what is known as the cyclotomic character. Gives you an embedding of this Galois group into this, right? Excuse me. So the degree is going to be equal to phi to the m if and only if the Galois group is equal to the whole, because these two are equal, right? So you're going to have equality here if and only if you have equality here. So that's a small observation. But let's now start proving the statements. So this is sort of done by induction on M. Okay. Well, let's see. So let's put U equal to zeta to the power P to the power M minus 1. That's a primitive pth root of unity because zeta is a primitive P to the mth root of unity, right? And being a primitive pth root of unity, when I take 1 plus u squared and so on, up to u to the p minus 1, I'll get 0. Because if t to the p minus 1 is 0 and t is not 1, the left-hand side here can be factorized as this, right? This is the left-hand side. And so if t is not 1, it's a primitive, then it has to be a root of this polynomial. And that's what I've written here. And let's put back the value of zeta, value of u, which is zeta to the power p to the power m minus 1. So you get this here. And that is the same as saying that f is a root of the polynomial, that zeta is a root of the polynomial f, where f is this. F of t is t to the p minus 1 times p to the m minus 1 plus t to the p minus 2 times p to the m minus 1, and so on, all the way up to the term just here is perhaps t to the p. So it has to be u, so which is p to the m minus 1. Yes, right. Okay. So now pi, which was defined as 1 minus zeta or zeta minus 1, what was it? 1 minus zeta. So because zeta is a root of this polynomial, f pi, which is 1 minus zeta, is going to be a root of this polynomial f1 plus t, right? Because if I put t equal to pi here, then I get 1 plus pi, which is equal to zeta, and f of zeta is 0. So pi is a root of this polynomial f1 plus t. Now, here is something that requires a little checking, and that's easy. It's not difficult, so I've left it to you. you check that this f1 plus t, this polynomial, f1 plus t is an Eisenstein polynomial of this degree. The degree is clear, the degree is here, but that it's an Eisenstein polynomial is not very difficult to check. Okay, now if it's an Eisenstein polynomial, then we get a certain number of things immediately, which we get that the degree of this extension has to be equal to the degree of the polynomial. The Eisenstein polynomials are irreducible, and when you adjoin a root, the degree of the extension is equal to the degree of the polynomial. But why is Kn equal to Qp pi? Because it's equal to Qp zeta, right? And zeta or pi was 1 minus zeta, or zeta minus 1, I don't remember, 1 minus zeta. Okay, so the degree of the field is this much, and pi is a uniformizer of Kn. Again, all this follows from that polynomial being Eisenstein. And the ring of integers is Zp pi, or which is the same as Zp zeta, because pi and zeta determine each other. Okay. Now, and the Galois group, of course, gets identified with this Z mod P to the M, Z star, the multiplicative group. Let's just abbreviate it by A sub M. So P is implicit, A sub M is the multiplicative group of Z mod P to the M, that ring, right? It's the multiplicative group. And for every integer V, we have similarly the rings AV, and these are not rings. These are the multiplicative groups of these rings. Okay, so it would have been, better to call them GM, but soon we are going to have a Galois group G, and then there's going to be a lower numbering. And I don't want this to be confused with this. So I'm now calling this A sub M, and A sub V. What is A sub V? It's Z mod P to the V Z star. Of course, there's a map from A M to A sub V, because there's a map from Z mod P to the M from this ring to this ring, right? Map meaning a natural homomorphism with the kernel. I mean, that comes from the whatever. You all know what this is. That was in the first lecture. In fact, when we defined ZP, we had discussed this kind of maps, right? Okay, so I'm now defining AM upper V. I mean, the V is a superscript to be the kernel of the map of the group from the group AM to the group AV. A sub M to A sub V. That's A sub M upper V. So if you want to look at a diagram, this is what it is. You have QP here, and then you have the field K P to the power V and the extension K P to the power M. The group here is A sub V. The group here is the group here is A sub M, and the group here is the kernel of the map from A sub M to A sub V, and that kernel is being denoted A sub M upper V. Of course, there's some small checking that, the map from A sub M to A sub V, in Galois theory, it is just the restriction. So sigma goes to sigma restricted to k sub p to the v. So one has to check that this is the same as this map here. Anyway, so that's not a, that's how things are. So the next proposition says that the ramification groups G sub u of the Galois group of Kn over K, n is, remember, p to the m, and u is any integer. I mean, why is it an integer? I think it can be any real number, no? U is any real number. Then the point is that, okay, so I mean, integer because I have not, then I have to say what happens between p minus 1 and p. So let's take it to be an integer for the time being, because integers, it's sufficient to define it for integers and then you get it for all reals, right? So this proposition says that the ramification groups G sub u of the Galois group of Kn over K is given by the inertia group is the whole of G. And that is fine because we know that Kn over K is totally ramified. Why is it totally ramified? Because Eisenstein, it's obtained by adjoining the root of an Eisenstein polynomial. So it's totally ramified. But if u is between 1 and p minus 1, then G sub u is yeah, you know, I'll allow u to be real, and I remove these minus ones here. Right, now it's good. Now I'm happier. So if I take u any real between 1 and p, but not equal to p, then G sub u is going to be equal to am1. am1 makes sense because I have defined amv for every m between 0 and m. And so on. I mean, if u is between p and p squared, but not equal to p squared, then this G sub u is equal to a2, am2. And similarly, and this goes on, if finally, if u is between p to the m minus 1 is greater than p to the m minus 1, then G sub u is am to the m, which is trivial. So what's the proof? Okay, I have a few minutes left, so maybe I can complete the proof. Yeah. So take any a which is different from 0 in am, and SA is the corresponding automorphism of k p to the m. I mean, this is the sort of the isomorphism Z mod p to the m Z star to the Galois group of k p to the m over qp. It's being denoted S going to S sub A. So SA is this automorphism, and let V be the largest integer such that A is congruent to 1 modulo P to the V. So E is the largest integer such that A belongs to A M to the V. That's what it means, right? Right. Okay, so I've written it here. On the other hand, what is JG of SA? Remember the definition of JG? It was the valuation of SA zeta minus zeta. So why this zeta is coming here? Because this O, K, P to the M, the ring of integers is O, it's not O anymore, it's ZP, is ZP zeta. So what is SA of zeta? It's zeta to the power A. So you can write it as zeta. I mean, this is equal to this. The valuations are equal because the valuation, whatever, Vk, P to the M of zeta is equal to 0, right? So you take zeta common and then you, its valuation is 0, so you can ignore it and you'll get this from that, right? But this zeta to the power A minus 1 is a primitive P to the M minus Vth root of unity. Why? Because A is congruent to 1 modulo P to the V, but not congruent to 1 modulo P to the V plus 1. That's how this V has been. So V has been defined as the largest integer which has this property, right? So it's not congruent to 1 modulo P to the V plus 1. So this thing is a uniformizer of this sub-extension. And therefore JG of SA is just the degree of this over this, right? Because K P to the M, K P to the M minus V, this is totally ramified. And therefore, the left-hand side is equal to the right-hand side. And this degree is, of course, equal to the cardinality of this group, because this is a group which is what? A, M, V here, A, V here. Of course, the whole thing is A, M here. Yeah, so, and that's the cardinality of this group, right? So, but if U is in this interval, then S of A, S sub A is in GU, if and only if V is greater than this C, this K has to be C, and therefore this GU is equal to this. So this last bit, you just need to just work it out what it means, and it should be clear. So I've taken 2 minutes extra, but let me just finish by, yeah, let me just finish here. Okay, we'll meet day after tomorrow.